We are recording. How's everybody doing? Doing good. Glad to hear it. Doing great. That's awesome too. That's okay. If we're doing good, we're doing good, you know. Okay. See what we can come up with. All right. Let's see. So first of all, so I am doing Open Lab on Thursday. So this Thursday, wow, I cannot spell at all. This Thursday, I will not plan a regular lecture. Instead, I'll be online, and you can come in, and we can work on programming issues together. You can screen share. If it's something in private, we can go into a breakout room and so on. But I'm going to basically use this Thursday as an opportunity for people to come in and work on code and so on, as opposed to doing a lecture on new material. We'll see if this works or not. Hopefully this makes sense. It sounded in the earlier section like a number of people were interested in having that opportunity. So, and we're down to like 10 people in our class session. So numbers are dropping in class, but I'd like to have an opportunity during class time to help people with code. So, you know, if you're struggling with PA1 on Thursday, we can certainly talk about that. But even if you're done with PA1, if you want to work on, you know, other things in code, or if you look ahead at PA2 and so on, it's kind of an open lab time. If you don't feel like you need open lab time, right, you don't have to come. I'm not taking attendance. There's no penalty for not coming to this, but it's just available as a resource. All right, let's so any questions on anything up to this point? How do we deal with division by zero? I'm trying to catch in my constructor, but I'm having trouble figuring out an elegant solution. I can't set numerator and denominator NaN since they are ints. True, but you can set yourself a flag. So you could have a flag in your class. That you turn on when you've got division by zero. You could simply decide, you know, any time that you need to know if you're dividing by zero, just check the denominator and see if it's equal to zero. And if it is, do something different, right? So if you're going to multiply two numbers, what do? You multiply numerator and denominator. If you're going to divide, you flip those around, right? But anytime you do something like that, before you do what we normally do with regular fractions, check to see if one of those is you know, not a number. And if it's not a number, just return not a number. So how do we do that? Well, you know, check to see if the first number has a denominator of 0. Check to see if the second has a denominator of 0. If either of those is true, return a fraction with a denominator of 0. And then in your two-string method, check to see if the denominator is 0, and if it is, just return NaN. And in your two-double method, see if the denominator is 0, and if it is, just return double.NaN. Right? So we can use denominator 0 as a flag, or you could set a separate variable as a flag. And there's probably other ways you can do it too. How would you suggest typecasting in the two-double function? Yeah, so certainly if you return double num over double denom, that will give you a double. I think in Java the deal is if one of those was a double and the other was an int, the int will automatically get converted. So it picks, you know, the highest precision variable needed to not lose precision. Cool. Um, if you decide that a denominator of 0 is going to be how you represent and recognize something that's not a number, you don't have to do a whole lot of checking. Like I say, for arithmetic operations, if any number involved has a denominator of 0, just return a fraction of 1 over 0. And then the only place NaN can be generated other than the constructor or by operating with a NaN is in division. And you could have two numbers that are valid like 1 and 0, and if you do the division operation, well, what's going to happen if you have, you know, 1 divided by 0? Well, this is 1 over 1. This is going to be divided by 0 over 1. You're going to end up with 1 times 1 over 1 times 0. You're going to end up constructing a new fraction like that. And the result's going to be not a number. You don't really have to do anything special there. But you do have to do something special with, say, subtraction. Because 1 over 0 minus 1 over 0, well, actually, maybe even with subtraction, you don't have to. But I would say anytime you finish an operation, check to see if the numerator is 0. Anytime you start, check to see if one of the things is not a number. And, you know, you can write methods that will help you do this. And you could write, you know, is a number as a method. You could say if is a number, parentheses, fraction, and so on. So you can structure it how you like. Anybody want to do a traffic light controller? No. Okay. Didn't think so. You figured out how to copy and paste in PuTTY. Awesome. That is a huge time saver. Share that on Discord if you like. From a standpoint of what you expect to see when you run the program, if we use your fraction class as the pattern to match your printouts, then that will be marked as success, right? Yeah, pretty much, although there might be some cases that I don't, that I check that I haven't listed in that sample main program. But yeah, that's the essential behavior. Here's a particularly aggressive thing that your program should be able to handle. I'm abbreviating fraction as frac for some reason. P equals new fraction 1, 1, so that's just the number 1 for I equals 1 to 1,000. P equals P dot multiply new fraction 1 comma 2. So multiply P by a half and then multiply by a new fraction 2. And do that a few thousand times. Right? So what should this do? This is 1 times a half times 2 will be 1 times a half times 2 will be 1 times a half times 2 will be 1. I can run this a million times. P should always end up being either a half or 1. Right? But if you're not reducing every time that you do an operation, this will blow up eventually, pretty quickly actually. Because you'll end up with a fraction like, you know, 16,000 over 16,000. And after 30 or 40 iterations, this will start doing strange things. So hammer on your code pretty aggressively. See if you can break it. Again, I'm totally okay with sharing your compiled fraction class with somebody and saying, try to break this. Or taking someone else's class and trying to break it with your own code. Or test it. See what it does. If you think this looks good. As long as you're not sharing source code, that's totally legit. You hung your traffic light controller on the wall. Awesome. Yeah, that's good wall art. All right, let's make a linked list class. Let's repeat some of the stuff we did in 222 in Java. For comparison and contrast, and as a refresher, and just as kind of an example of sort of a larger implementation of something in Java, let's put together a linked list class. Now, for PA2, we're not going to use our own linked list class. We're going to use the supplied linked list class and the hash map class and other things like that. But let's see, if we had to build linked list by hand, what would we do? And then we're going to play with this, and this is going to lead us into working with the actual linked list class, and it'll lead us into topics about generics and other things. I have a... oh good, they're done backing up. It's been surprisingly quiet this quarter out here. We'll see how that holds up. Alright, so let's write some code. Alright, let's start with a main program. Alright, so I got my public static void main, as usual. What should we call our linked list class? Potato. Okay. Alright, so that's our linked list class. Yeah, I did mean potato. Alright, so let's construct an empty potato, right? So we'll just call the constructor. We've got an empty list. Add some things to our list. Alright, so we're going to add 5 integers to, oh yeah, totally. We're going to add 5 integers to our list, and then let's print out the contents of our list. So we're going to write a print method, and there's our main program. Alright, we can go home, we're done, right? Haven't really done anything here, but we're assuming that we have traffic on the bridge. That never happens, right? So we're building a linked list class, and this is just the main program to drive it and test it. So standard main program, and construct our list, use the add method that we're going to write to add some numbers to it, and then the print method to print out the contents. Alright, so let's go ahead and actually make the linked list class, which we're calling potato. So what do we need for a linked list? What are the variables that are going to be involved? And there's really only one. So the node's going to have an int and an x. What about the list itself? One step up from the nodes. And this isn't required, but we always did this when we made linked lists. Sentinel. Alright, so we're going to have a sentinel. And the sentinel is going to be a node. Okay, I'm just going to call this a node so we don't get too extreme with the naming. So we're going to have a sentinel that's a node. And when you want to create a linked list, really all we have to do is create a Sentinel node. Right? So I'm going to make a constructor. And the constructor is just going to initialize the Sentinel by calling the nodes constructor. And that's pretty much all we got to do. No, trying to write potato. All right, so let's do our node class while we're in here. And so, so we already got the answer to this earlier. A node's going to have a piece of data, which we're just going to stick with integers. And then it's going to have a next field. So what kind of thing is the next field? It's an address. It's a node. Right? That's all there is to a node. And this is a little different from writing this in C, where we had struct node stars and ampersands and stuff like that. The data is an object of type int. The next is an object of type node. And this is totally legit to Java. The compiler will not have a problem with, using a node inside a node. That's totally cool. All right, so that's a node. We could make a constructor if we wanted. Let's make a constructor. So this will be public node. And we're not going to pass anything to this. But we'll go ahead and we'll set the next field equal to null. Actually, let's pass a value to this. So we'll set data equal to value. So we can construct a node, but we can pass a value to it, and it will give that value to the data piece of the node, and then the next piece will always be initialized to null. Yeah, // is a comment. All right, so there's our node class. Let's go back to our linked list class, our potato class. Let's write this add method. You need two constructors. I'm just going to treat the Sentinel as a plain old node. I'll just construct with a value of 0. Because we don't use the data value. Now I could make a constructor with no argument, and I could give the node a particular value. That would mean the Sentinel. That might be a cool thing to do. All right, I'm going to do a simplified version of this. I'm just going to add to the beginning of the list. So if this is what our list looks like, and this is the Sentinel, and we create a new node, we're always going to insert it in the beginning. So we're going to change this new node to point where the Sentinel is pointing, and then we'll change the Sentinel to point to our new node. Because I don't feel like searching down the list and alphabetizing or sorting and all that kind of stuff. So to add, basically we're going to create a new node, have it point where the Sentinel points, and then change the Sentinel to point to the new node. And that's basically 3 lines of code. It's 3 sentences to explain, it's 3 lines of code to write. So this is a public method, doesn't have to return anything. And so we're going to make a node temp, which is a new node, whose data value is, you know, data. And then temp.next equals sentinel.next. And sentinel.next is going to equal temp. There's our add method. Alright, let's print the contents of the list. So public void print. Doesn't need to take any arguments, doesn't need to return anything. Let's start with the node that the sentinel is pointing to. And while this is not null, let's go ahead and print out temp.data. And then move down the list. There's our print method. Alright, so this is our whole linked list class, right? It's modularized. We're not, you know, doing the nitty-gritty node stuff in here. Well, nodes aren't that complex. We set the data field, right? But the sentinel, we just make a new node. To add an element, we make a new node. We have it point where the sentinel points, and we change the sentinel to point to the node. To print, we start with the first actual node of the list, or null if the list is empty, and as long as we're not at the end of the list, we print out the data field, and we move to the next node. And a lot of what we do in Java is going to feel this straightforward to us, right? If we're breaking things correctly into classes, and we're using objects the way that we kind of feel like objects should be used, this will start to feel very, very natural and very comfortable, right? Not a whole lot of trying to remember, should this be, you know, a star or an ampersand or a star star or a bracket bracket or things like that. It almost starts to write itself at some point. Alright, so let's see if this actually compiles. Let me do this with a couple of windows here. This is not the first time I've done this quarter. So our Java files are called .java. Alright, there you go. So we inserted 1271, 1111, negative 11, and 95, and when we printed them out, they came out in reverse order, right? Because we're inserting at the beginning. It's a FIFO type structure, right? But there's our linked list, and it totally works. And, you know, it's a handful of lines of code. Okay, now suppose we wanted a linked list of strings. Suppose instead of adding numbers, we wanted to do this. All right, we've changed our main program. That was easy, right? We want to add strings. We're obviously going to have to pass strings to our add method. But what else has to change? So let's look at our linked list class. Down here, when we construct our sentinel node, we need to pass, a string. So I'll just pass quote, quote, because we're not going to use the value in the sentinel. The add method, this has to be a string. That's pretty much it. I had to change the word int to string right here so that I can compile this and it knows when I pass a string I should run this code. And I had to change, how I constructed the sentinel node. But that's probably it for the linked list class. And in the node class, I'll just change that to a string. And so we can compile this. Oh, and I have to change this to a string. That's the big change because we're trying to store a string in our node. So I'll change that and I'll run it. Oh. Well, that was going to be a glorious demo that didn't work. There we go. So now we inserted a bunch of strings and they got inserted in inverse order because it's FIFO and bingo, we've got a linked list of strings. And the essential point here is that, to change from integers to strings, I didn't have to rewrite, the mechanics of a linked list. I didn't have to do something fundamentally different to create a node or put it in the sentinel or traverse the list and so on. I really had to change the word int to the word string in a few places. I had to change what I passed to the add method and so on, but that was pretty much it. And so someone just asked in chat, is there a way to overload so whatever is passed in works? Basically. So there's a concept called a generic. And a generic is a way to define what we've been doing here, but to write code where, maybe we want to use strings, but maybe we want to use ints or hash maps or something else. And instead of having to go in and change the word int to the word string, right, we can make that thing basically a variable. And we could use one set of code like what we have here for a linked list, but say I want to use this for ints, or I want to use this for strings, or I want to use this for doubles. And it will all kind of work automatically. And so yeah, that would kind of be like, the equivalent of a type def. It's going to basically let us use a symbol instead of an actual word here. And then in our main program, say anytime you see that symbol, use the word string or use the word int. That's the behavior of it. The mechanics for making that happen are a little different, but that's the effect of it. All right, here's the magic part of it, okay? This is really good stuff here, right? Let's make a linked list of rectangles. So I dug up from the Linux archive that we've got going our old rectangle class friend from week 1, right? So there's a rectangle, we can construct it with a I don't have a constructor here. We'll put a constructor in here, right? But we can multiply rectangles, we can print out the area of rectangles, and we can print out rectangles, and it prints out meaningfully, right? So let's just add a constructor. You don't need a constructor. There's always a default constructor, but if I don't write a constructor like this, then when I want to make a 3x5 rectangle, it's multiple steps. I have to construct a new rectangle and then set its length and set its height accordingly. Like this, I could just construct a rectangle and I could specify the length and height right there. And it also lets me do something like make a constructor where I have, you know, just one argument so I can make a square in particular. And I'm just going to get rid of my bizarre multiply routine. Because that was just something we did. I'm going to fix my typos. All right, so we're back to where we were last week. We have a rectangle class. Yes, thank you. I should just check my chat before I look for typos. So here's our rectangle class. All right. Suppose we wanted a linked list of rectangles. Okay, so if someone gave you this assignment, it would be like, oh no, I'm going to have to do all this work, right? It's not bad. So I'm still going to have my linked list. I'm going to create an empty linked list. But this time, what am I going to add? I'm going to add a 3x5 rectangle. And I'll add a 4x6, and I'll add a 2x3, and I'll add, you know, a 9x9 square, and I'll add a 1x7. All right. So I'm making a linked list of rectangles. Why not? All right. What has to change in our linked list class? Well, you know, I got to change my sentinel. So I'll just make, you know, a 1x1 rectangle for the data value of the sentinel node. Why not? And my add method is going to take a rectangle. And that's pretty much all that has to change in my linked list. And in my node class, this is going to be a rectangle, and the thing I passed to my constructor is going to be a rectangle, and that's kind of it. I didn't change any other code, I didn't change any logic, any looping, nothing like that. So I'll recompile everything. I'll fix my typos. And when I run my main program, there's my linked list of rectangles. Right? It could not be more straightforward. And I didn't even have to change my print method. Right? What does my print method do? Well, it takes the thing the sentinel points to, it loops through until there's no nodes left, and it just says print the data field of that node. Well, the data field of that node happens to be a rectangle, and print line is expecting a string, and so the toString method of the rectangle is called, which returns, you know, this string that has the dimensions of it with some other words, and that's what gets printed out. And it all just kind of works, and this is quintessential object-oriented programming, right? Because the rectangle class was this kind of self-contained thing that, you know, lets us construct and lets us print by using toString and so on and so forth, we can use it just like a string or an int or a double or anything else. All right, so this is what I want you to focus on when you're contemplating this stuff on, like, you know, long walks or whatever. And also when we start working on PA2, right, this is the example to come back to. the fact that, you know, we're able to use another class that we built, the rectangle class, inside this class, potato, right, or linked list, and it's no different from using a string, which is another type of class, or an integer, which is, you know, it's a primitive, but it's basically another type of class. We're just using objects, and objects come in all different types, but they're just objects. So down here, you know, the pieces of a node are data and next, right? That's the top and the bottom of the node rectangle that we always draw. And the constructor, I passed in a value to assign to the data, right? Which I called value, so I set the data field equal to that. And I just decided for convenience, I would always set the next field to null. And then if you want it to point somewhere, you can change what that next field is. Cool. All right. So being able to use objects of different types, right, without having to worry about all the details of that object, that's a key to object-oriented programming. And in my print method, you know, if I wanted to, you know, print out the area of the rectangle stored in my list, I would just print temp.data.area paren. Now this doesn't work if you know, we're going to switch different data types, but if I'm just working with rectangles, I think I have an area method in there. Right? Because temp.data is an object of type rectangle and rectangle has an area method, this thing has an area method, so this thing dot area paren calls the area method. So this is super duper powerful, right? Because when we have an object, a variable, we've got a lot more than just the value of that variable. We've got all the code that goes along with it as well. And we can call that code by just using, you know, the name of the variable or the reference to the variable, in this case temp.data. Right, and we can go from there. So there is a linked list class built in to Java, right? It's a class we can get to by doing what's called an import statement. And let's look at this page in a little more detail than we've been doing. So this is the linked list class. First of all, up here at the top, there's this angle bracket E. Okay, a linked list takes what's called a generic type. When we construct a linked list, do we want a linked list of integers or strings or rectangles? We get to specify that, right? And we're going to actually say, you know, linked list, angle bracket, and a type of thing that we want the linked list to hold. Okay, we're going to basically put in the name of a class there. And if we say integer, it'll be a list of ints. If we say string, it'll be a list of strings. If we say rect, it will be a list of rectangles. And the reason we can do this is because the underlying logic of a linked list is not affected by the type of thing that you're putting in there. All right, the next thing to notice here is this hierarchy. This page describes what's called a linked list. It comes from java.utilities, right? But a linked list is actually a particular type of what's called an abstract sequential list. And an abstract sequential list is a particular version of an abstract list, which is a version of an abstract collection, which is a version of an object. Yeah, for a linked list, we would have to use integer with an uppercase I, exactly. But then we can still just plug in regular ints and stuff. So there's this hierarchy, and we'll spend some time talking about this later, but this is basically the idea that part of the idea of object-oriented design is not having to reinvent the wheel. So if somebody has already made a class that does some of what you want, but you want to extend that, add some additional features, change some features, you don't have to start from scratch. You can actually start with an existing class and make an extension of it. And in an extension, you can add new methods, new fields. You can change methods and fields from the class that you're extending. And this is how a lot of the Java packages are built up. They're extensions of other classes. So in this case, linked list is an extension of an abstract sequential list, which, you know, has its own documentation and its own thing, and an abstract sequential list is an extension of an abstract list, which looks like this. And an abstract list is an abstract collection, which is a little simpler. An abstract collection is actually an object. An object has a manual page. And objects are the root of the class hierarchy, right? Everything is an extension of an object. And it's got, you know, a small set of methods you can call. And this one is particularly useful, clone, which lets you create a copy, or equals, which lets you know if two objects are the same, and so on. So let's look at the linked list class. We'll talk about extensions on their own when we get to doing graphics and GUIs, because we'll have to do extensions there. So this is the hierarchy of it. It tells you, you know, E is the type of elements held in this collection. And then there's some words describing it. So this is saying that it's doing a doubly linked list. So we have forward pointers and backward pointers. Irrelevant to us, right? Because we're never going to access those pointers directly. This is information hiding. This is encapsulation. We're going to see a series of methods we can use to interact with the list down to some firewall. And below that is all internal details. The fact that it's a doubly linked list, that's irrelevant to us up here. We're not going to say, you know, give me the forward pointer, give me the backward pointer. Tell me if this pointer is null. That's hidden from us. Those are implementation details. Our interface to the linked list will be this very well-defined set of methods that we use to, you know, search and add and initialize and delete and so on and so forth. But under the hood, it's a doubly linked list of what are called the queue and DQ, the list and DQ interfaces. A little note here that this is not synchronized. Later on in the course, we'll be working with threads and running multiple processes simultaneously. And when you have two or more processes sharing memory, you got to be really careful. We can get into all kinds of subtle and interesting complications if two things, for example, try to modify a memory location at the same time. So some classes will have methods that are safe to use from multiple threads. Some are not safe, okay? Linked lists, the methods in here are generally not safe. So we have to do things ourselves if we might have two different processes trying to modify the same linked list at the same time. So there's detail up here, you know, written out, and then we get into kind of the standard structure of this. So constructor, there's two ways to construct this. The way we'll usually use just linked list, and makes an empty linked list. And then all the methods we can use. So what have we got here? We've got the ability to add something to the end of the list, add something at a particular position, add something in the beginning of the list, remove all the elements, make a copy, see if an element is contained in the list, and so on and so forth. And there's all this stuff that we get once we make a linked list. And these aren't all, you know, totally linked listy. For example, you know, being able to return the size of a linked list, well, that's not something that we normally, you know, think of with a linked list. Being able to replace an element at a particular position in the list with another element, that's not very linked list-like, right? But it's very useful. Now, if we don't want to do that, we don't call that method. But that's available for us when we create a linked list. Splitterator creates a splitterator over the elements in this list. Actually, don't know what a splitterator is. Reports splitterator.size and splitterator.ordered. Oh yeah, obviously. But that's a cool name. I don't know what it does. We can push and pop, and we can remove the first element and remove the last element, and so on and so forth. Right. So these are you know, the ways that we interact with a linked list. And iterators, we touched on in 222, right? The idea that if we just wanted to print the contents of this list, we could, you know, make a print method, and it would print each element of the list separated by spaces. But it's very unlikely that's exactly what we want to do. Maybe we want to print one element per line. Maybe we want to print inside angle brackets with commas in between. Maybe we don't want to print anything except, you know, the middle 15 elements or something. So we need a general way to be able to go through the elements of a data structure one by one, and that's not always clear how we can do that. Now for a linked list, there's a way we could do that. We can ask for the elements at a particular position, right? We can say get the element at some index. But for something like a hash table, there's no such thing as the first element or the third element or the last element. There's no natural order to the elements. So we need some way to go through the elements of a data structure, and that's what iterators are for. And we started talking about this in 222, so we'll talk more about this later. But basically, we have all these methods available to us, and they're all part of a linked list. And then, because, you know, a linked list is an abstract sequential queue, which is an abstract list, and so on, we have other methods that are provided by these classes that we extended, right? Including things like equals, and so on, that are inherited from elsewhere. Oh no, the evil splitterator. All right, and then there's, you know, the more detailed description that you can click through on each of these methods, and that's our Java documentation. So we'll play with linked lists tomorrow. We'll go ahead and you know, dig into this idea of a generic and make linked lists using this class and see how some of these methods work, and then we'll play around with iterators because that's useful. There's also a toString method in here. Now, it's not defined as part of the linked list class, but it's defined in one of the things that linked lists extends, which is an abstract collection. And so in that class, there's a toString method. And the toString returns a string representation of the collection. The string representation consists of a list of the collection's elements in the order given by the iterator, enclosed by square brackets, separated by commas and spaces. And they're converted using value of. So this is a particular toString method. If that happens to be what we want our linked list to look like when we convert it to a string, we're all set. If not, we can write our own toString, and it will override this toString. So part of working in Java or any object-oriented language is understanding these mechanics of class extensions, right? Being able to take an existing class and make changes or improvements or modifications to it, right? And then language-specific constructs like generics for being able to write one class once that works with different data types, and so on and so forth. So we'll be working through these things in the coming weeks. PA2, you're going to be working with linked lists and hashes and some other things, and doing some parsing and so on and so forth. All right, two-double method turns a fraction into a value. Yep, that's correct. So if you have 1 over 2 and you call the two-double method, it should return the double precision number 0.5. And you can use casting to do that. So if you have an integer n and an integer d, if you return n over d, well, n and d will get divided as integers, and if it's 1 and 3, it'll return a 0. But if you do a cast, if you put the word double in parentheses before n and then divide by d, that'll turn n into a double precision value version of itself, and that'll be divided by a double precision version of D, and so if that was 1 and 3, you would actually get, you know, the double 0.333. So you can do casting there. All right, we are out of time. I will see you next time. Have a good afternoon. Take care.